Hello students, in this video we'll discuss the convergence of infinite products of holomorphic functions. Let's suppose we have a sequence of holomorphic functions on a set omega, and we have this series over here, and we have the sum n goes from 1 to infinity of fn of z minus 1 converges absolutely and uniformly on compact subsets of omega. Then the product n goes from 1 to infinity of fn of z converges absolutely and uniformly to f of z, which is holomorphic on omega. And moreover, f of z will be equal to 0 if and only if a finite number of terms in this product are 0 at that point. And f of zeta equals 0 if and only if a finite number, and that's important, it's a finite number of fi vanish there at zeta. Excellent, okay? So the proof comes down to a couple sort of elementary lemmas, right? So let's do the first lemma, right? So how do I prove this? And this is a beautiful result, right? Because what this tells me is it says if I give you a sequence of holomorphic functions defined as set omega, there are conditions under which if I multiply all those functions together and take the limit, the resulting function will still be holomorphic, right? And I can write down the 0. So this gives me a way of extending the idea of the fundamental theorem of algebra, which is if I give you a polynomial, just factor it, right? Factor out by the roots. I can do the same thing now with functions that have an infinite number of zeros by this result, okay? Excellent. So let's do it. So what's the idea? So the idea is the following. We need the first lemma. So lemma 1. If fn converge uniformly to f on a compact set. So the double arrows mean uniform convergence. K, a subset of omega. And if the real part of f is less than or equal to a on that set, then what can we say? Then we can say that the exponential of fn converges to the exponential of f. And this is going to be important for us in the proof, right? Of course, what do we know? We know from undergraduate analysis, undergraduate real analysis, that if I give you a sequence which converges uniformly and I apply a continuous function to that, uniform convergence isn't guaranteed, right? I need other conditions, and that's the condition I need for this one, okay? So let's do it. So how do I prove this? So here's the proof of lemma 1. Okay, so let epsilon be greater than 0 and pick delta such that e to the z minus 1 is less than epsilon times e to the negative a if modulus of z is less than delta. That's the continuity of the exponential, right? That's near 0, right? Okay, and now pick n such that if little n is bigger than big N, we have what? We have fn of z minus f of z less than delta, right? That's the uniform convergence. Now I've used uniform convergence over here. I've used this condition now. Good. Okay, and so now what does this tell me? Well, okay, well that's a value of z. So this tells me the following. It tells me that the exponential of fn of z over the exponential of f of z minus 1 is less than epsilon e to the negative a. Multiply by exponential of f of z. This tells me exponential of fn of z minus exponential of f of z is less than what? Well, it's less than epsilon e to the negative a times the largest that the modulus of exponential of f of z can be, which is what? Which is the exponential of the real part, right? And the exponential of the real part is what? It's bounded, right? So this is going to be e to the a, which is just epsilon. And we got it, right? So I have proven that there's uniform convergence of the exponential. Excellent. Now let's go on to the proof of the theorem, right? So let me recast it in the traditional way so we can use ordinary estimates, okay? So let's suppose, let's call this another lemma over here, lemma 2, which will be the, in some sense, a different proof, and we'll just cast lemma 2 in lemma 1 sense. Okay, so suppose that we have what? Suppose I give you a sequence, n goes from 0 to infinity, of Gn of z. And let me suppose this converges absolutely, and uniformly. Okay? Then what can I say? Then I can say that the product, this implies the product, n goes from 0 to infinity, of 1 plus Gn of z converges absolutely and uniformly. Okay? Excellent. Okay, so if this converges absolutely, there exists proof. There exists an n such that if n is bigger than or equal to n, what can we say? It converges uniformly and absolutely, so I can say that Gn of z less than what? Strictly less than a half, because the series is convergent, right? So it's strictly less than a half for all z in a complex set k, right? For z in a complex set k. Well, if this is the case, then what can we say? Then I can say that we know that the log, this implies that the modulus of log of 1 plus Gn of z is less than or equal to a constant times Gn of z in that set, because you're over here where you're less than a half, right? So I think the actual constant is 3/2. We put that in our previous video, Gn of z. And that proves that this thing over here, this proves that the sum k goes from n plus 1 to infinity of the log of 1 plus Gn of z converges absolutely and uniformly. Great. Now, since that's the case, I can apply lemma 1. By lemma 1, so does the exponential. So it converges something, the function h of z, which is going to be what? Which is going to be the sum k bigger than or equal to n plus 1 of the log of 1 plus, that should be a gk, right? gk of z, like that. Implies that the exponential, of h of z is going to be what? The exponential is just going to be the what? The product k bigger than or equal to n plus 1 of just these 1 plus gk of z, 1 plus gk of z. Great. Moreover, the exponential of h is not 0, right? And so this converges to this. This is a uniform convergence, right? So this converges uniformly, right? So this is a uniform convergence. Excellent. And so now what does that allow me to do? That allows me, the first couple terms of the product are automatically convergent. It's a finite number, right? So now I can say what? I can say 1 plus g1 of z, 1 plus gn of z times the product k bigger than or equal to n plus 1, 1 plus gk of z converges absolutely and uniformly. In k. Good. And moreover, I know that this term over here is what? This term over here is the exponential of h. That's the exponential of h of z. And the exponential of h of z is never equal to 0, right? Which means that the only way there to be a 0 of this function over here, the product of this function over here, is if the root, it occurs as a root over here, a finite number. Perfect, right? And so that proves the theorem. And so now what can we do? We can apply our result. So typically it's written like this. It's written with a -1. So what I wanted to do is in some books, they do fn minus 1. In other books, they do 1 minus fn. In other books, they just do straight g, right? So I want to give you both perspectives, and we can apply this now. I can apply this now with what? With gn of z is equal to fn minus 1. Done, right? If we apply, so if gn of z is fn of z minus 1, then what can we say? Then that turns into what? Then that says the product n bigger than or equal to 1 of fn of z converges. Absolutely plus uniformly. Excellent. So now what I know is I know that if I give you a sum, which we can typically handle, right? A sum that's converging absolutely uniform, which we have the good things for. We have like the Weierstrass M-test. We have a whole bunch of great tools for that. We have a great number of tools for sum comparisons. So if that sum converges absolutely uniformly, the product, the infinite product, 1 to infinity of fn of z, converges absolutely and uniformly. And moreover, I know the structure of the zero set. The structure of the zero set is if a definite number of the factors of this product has to vanish if the whole limiting function, the whole infinite product, vanishes at that point. And we'll see in further videos how exactly do you construct these functions fn in a way that gives you a canonical way of representing entire functions. Thank you very much.